Alright guys, for this first video we're going to talk about how to write a balanced chemical equation. Kind of sick today, so if you hear me coughing, just bear with me. So we're going to start out with just your basic chemical equation here. So let's say, let's do the decomposition of water. So okay, in any chemical equation that represents a chemical reaction, you have what's called reactants. Okay, and they're named that because the reactants is what reacts, right? In which case, in this reaction, it's just water decomposing. And you've got products. And products are what is produced. Okay, so reactants and products. So you start out with the reactants, you end up with the products. So that's the first step in knowing how to write a chemical equation. The next step is to understand all the different symbols. So the first symbol you'll see is this arrow right here. Okay, really, and I'm going to make a chart here for all the symbols. Okay. So the first symbol is going to be the arrow. And what it basically means is it's what the reaction yields, or what the reaction produces. Okay, so water decomposing, which it really decomposes through something called electrolysis. You know, obviously, if you leave a cup of water out, it's not going to spontaneously burst into nitrogen and oxygen. Anyway, the arrow means yields or produces. So it's the reactants producing the products. Okay. The next symbol would be, I guess, this plus here. Plus just means and, basically. Okay. So in this case, water decomposes to produce hydrogen and oxygen. Okay. So plus, we will just say means and. Okay. Another thing you might see. So I'll do it over to the side. So let's say you have, let's do the burning of magnesium. Okay, the burning of magnesium. So magnesium, as you've seen before, is a metal. It's a solid. So we have what's called a phase symbol that you put as a subscript. You put a little S down there for solid. Oxygen, O2, is a gas. And the magnesium oxide is in the room here, but it's also a solid. Okay? So up here, we would say water's a liquid that's going to decompose into two gases. Okay? So basically, what I'm trying to get you to understand is that these three, and for some reason they use the curly L. I don't know why, but that's what it is for liquid. So G, S, and L is gas, liquid, I'm going to abbreviate, and solid. Okay. The other one you might see, let's do another reaction here. Let's say we have hydrochloric acid reacting with sodium hydroxide to form table salt and water. Okay. The hydrochloric acid that you would be using in the lab is not pure hydrochloric acid. Okay, it's diluted. All right, which means it's really just dissolved in water. In chemistry, we call it dissolved in water. It's dissolved in water, we call it aqueous. AQ. The same goes for sodium hydroxide. It is dissolved in water. Okay. In this case, in this particular reaction, the salt that's produced is going to stay dissolved in the water. So even though salt itself is a solid, in this reaction, it will be aqueous. Water, however, is a pure liquid. Okay, so the next symbol for you guys, AQ, stands for aqueous, which means dissolved in water. Okay? So it's dissolved in water. Another thing you might see, let's go back up to the burning of magnesium over here. Let's look at this reaction over here. All right, so if you're in my class, you saw the reaction we did with magnesium. I can't just take the piece of magnesium metal, hold it up in the air, and it randomly bursts into flames with the oxygen, right? I had to add something. I had to add heat. When I did that, or in a chemical reaction, when you write this, you write it right there. Okay? So that's kind of showing that you need heat for this reaction to happen. It's not going to spontaneously happen without the heat. Okay? So, let me put this down here. So anything that a reaction needs, heat for example, you would put on top of the arrow. Okay? There's something else called a catalyst that we're going to talk about later. If there is a reaction catalyst, you would put that on top of the arrow. It just means it speeds up the reaction. Okay, so those are the basics as far as how to write an equation. But there's a couple more things that we need to get into. So let's go back to this equation with hydrochloric acid and sodium hydroxide. Okay. So there's our reactants and products. So there's something we talked about earlier on in the year called the law of conservation of mass. Okay. The law of conservation of mass. Okay. And what the law of conservation of mass basically says is, at least applied here, you have to have the same amount of mass before the reaction as you do after the reaction. So we're going to split the reaction here between reactants and products. You got to have the same amount of mass before as you do after. It also means you have to have the same amount of atoms of each element before the reaction as you do after. So before the reaction we had, I'll start with sodium, we had one sodium atom right here. So then it makes sense that after the reaction we still have one sodium atom. It just switched places. We have one chlorine atom before, we still have one after. We have one oxygen before, we have one oxygen after. We have two hydrogen atoms before, and we have two after. So the number of atoms of each element stays the same. Stay the same here, always stays the same. It just switched places. That's what happens in a chemical reaction. You don't have atoms getting created out of nowhere. You can't. That's just not how it works. So this is basically the law of conservation of mass and why it's important. However, let me show you another chemical reaction. Let's go back to, tell you what, let's go back to magnesium and oxygen reacting to make magnesium oxide. Okay? So if we break it down like we did before, and we count it up, one magnesium, 1, 2 oxygen, 1 oxygen. So we got a problem here, okay? Our reaction is not balanced, right? So basically we are going to need to balance this thing. So the way you do that is, if you have magnesium and oxygen reacting, then you're going to need to produce more product oxygen, if that makes sense. Let me show you what I mean. So let's draw out the little molecules here. This is by no means a technical drawing. So you have magnesium, and you have O2, and you have MgO. Okay. We need more oxygen on the product side. So we're going to have 2 MgOs. Okay. So now our oxygen is balanced. We have 1, 2 here, and 1, 2 there. However, magnesium is not, so we need 1 more magnesium on the reactant side. So that's how you balance an equation. You can add coefficients in front of the compound or element to show how many of that compound or element you need for the reaction. So basically, you need we'll say moles, 2 moles of magnesium, 1 mole of O2 to produce 2 moles of MgO. You see how that works? Okay, I'm going to give you guys a few examples, and we're going to practice this balancing a little bit, because this is really important. So, the first example, let's do water. Let's start easy. Water decomposing again. So H2O decomposes to form hydrogen and oxygen gas. And we're going to ignore those phase symbols right now. So go ahead and try to balance this one. Pause the video, give it a shot, unpause, and you'll see the answer. Okay, so to balance this one, all you got to do, and I'm not going to draw pictures anymore, but feel free to do it if it helps you. I do think it's a good idea. 2 there, 2 there, and it's balanced. Okay, but it can get a little harder than this. This one that we've been doing has been pretty basic. So let's say we have hydrogen gas reacting with nitrogen gas to form ammonia. Okay, so if we do it like we did before, we can see that we need more hydrogen on the reactant side. We need more hydrogen over here, okay? Because we have 3 on the product side and 2 on the reactant side. However, we're running into a problem here, because if I add more, I put a 2 here and add more, that gives me 4. Okay, and I've got 3 on the product side. So there's no way, there's no number that I can add here to give me 3. So this is where we run into a problem, which is kind of brings me to the next point. When you are finding the number to put there, put the coefficient there, what you're really trying to find, okay, you're trying to find what's called the LCM, the least common multiple, to balance the equation. Okay, and what I mean by that is the least common multiple that would give you the same amount of hydrogen, in this case, on both sides of the equation. Okay, so we're looking for the least common multiple of 2 and 3. The lowest number that you could multiply both of those to reach, which is 6. Okay, so we need to put the coefficients on each of those compounds in order to get 6 hydrogens from each. Alright, so over here with the first one, we can put the coefficient of 3 to give us 3 H2s, which is 6 hydrogen. Which means over here, we put a coefficient of 2 NH3s, which also gives us 6 hydrogen. And coincidentally, well, not really coincidentally, nitrogen is also now balanced. We have 2 on each side. Okay. So let's do a couple more examples. Let's do, we have some aluminum, and it's going to react with oxygen to form aluminum oxide. So balance that one. And let's say you have potassium iodide reacting with lead nitrate. Okay. Reacting with lead nitrate to form potassium nitrate and lead 2 iodide. So go ahead and try to balance these. Pause the video and then I'll show you the solutions. Okay, to balance this one, let's do the first one first. First step, we look at aluminum. We have 2 in the product, so we'll need 2 in the reactant. Okay. Now with oxygen, we run into the problem we had before, where we can't make 2 on the left side equal 3 on the right side. So we're going to have to do the least common multiple. Least common multiple again is 6, so we'll put a 3 here, a 2 there to get 6 oxygen. But now we've got 4 aluminum on the product side. So to fix this, they're going to need to change this to as often happens when you're balancing equations, and then add a 4. Okay, so that first one is now balanced. So for the second one, and this one probably looks kind of nasty if this is your first time balancing equations, because you've got the parentheses and the polyatomic ions. So it's really not that bad, I promise. We're going to split it down the middle. So let's count up our elements. We have 1 potassium ion atom on the left, 1 on the right, 1 iodine on the left, 2 on the right. So right off the bat, we know we have to put a 2 here to fix the iodine. Okay, now we've unbalanced potassium, so let's fix that over here. Right? So now potassium and iodine are good. We count lead. We have 1 on the left, 1 on the right. We count. See, now here's an interesting situation. You could break down nitrogen and oxygen and count them separately, but in this case, they're only present as the nitrate ion. So we could say we have 2 nitrates on the left, and now we have 2 nitrates on the right. So we're balanced there. So this equation is now balanced. Just took a couple of 2's. All right, guys. There's plenty of other examples online if you want to go look out there, but this is kind of the basics to it. So go practice.